people really busy with midterms nowadays? Yeah, it's tough. Hopefully the quiz is not too stressful for you in this class. It's not meant to be, but still just review the homeworks and the sample quiz from last semester. You should be able to do well. Okay, why don't we start with, I just wanted to make sure, oh wow, what happened here? Okay, so I just want to make sure from the last lecture that you understood the summary. Okay, so last time we talked about non-idealities in an MOS system. And so one of them was oxide charge. Any fixed charge or interface trap charge in the MOS system, in the oxide, will shift the threshold voltage of your CV curve. Okay. But there are two other non-idealities. One is gate depletion, where the gate, if it's heavily doped polycrystalline silicon, it doesn't really truly act as a metal. It can actually become depleted a little bit, and that effectively increases the dielectric thickness of your MOS stack. The other effect is the fact that the inversion layer and the accumulation layer each has some non-zero thickness. So when you're forming an inversion layer at the oxide interface, it's actually located about a nanometer or so away from the interface. And the more gate voltage you apply to attract the inversion layer to the surface, the smaller that inversion layer thickness is. Or the more negative your gate voltage is to attract the accumulation layer, then the smaller the thickness of that accumulation layer. So just wanted to clarify that the difference. So here's the ideal. The solid line is the ideal. And the difference between the ideal case and the measured small signal capacitance, okay, just to summarize, what is that due to? What I've indicated here. Quantum, yeah. So this is due to, this difference is due to, in this case, it would be the accumulation layer thickness being greater than 0, right? So when you're changing, when you make small changes in the gate voltage, you're adding and subtracting charge from the accumulation layer, but the accumulation layer is actually located like a nanometer away from the oxide thickness, oxide interface. So the equivalent dielectric thickness is a little bit thicker. So the small signal capacitance is lower. And notice that this difference gets smaller as you go to more and more stronger gate bias, right, to pull the accumulation layer closer to the oxide interface. The same thing here then, on this side, so this difference here is due to the inversion layer thickness. That thickness is greater than, being greater than 0. Okay, so notice again, compared to the ideal, this measured CV curve gets closer as the inversion layer thickness gets thinner, so the effect of the non-zero inversion layer thickness gets reduced. Okay, and finally, in inversion, okay, so in this regime, we're talking about inversion. Surface is inverted. We actually see this smaller gate capacitance, small signal capacitance compared to the ideal CV curve because of the gate depletion effect. Okay, so let's do black. So this slope is due to the gate depletion effect. And then, so as you increase the gate voltage to the right, as you bias more strongly into inversion, the gate is becoming more and more depleted. And so you're increasing effectively the dielectric thickness as the depletion width in this gate increases. So that causes the capacitance to go down with increasing gate voltage. But the effect of the inversion layer thickness becomes less as you go to higher gate voltage. Okay, so that's why the spacing between this black line and the measured data goes down. Okay, so qualitatively, you should be able to explain these why a CV curve, a measured CV curve doesn't match the ideal basic CV curve. That's basically all you need to know for like a quiz or a final exam. Okay? All right, any questions about non-idealities in an MOS capacitor? No. Yes, Ali? Okay, so the question is, because there's depletion on the, okay, so in inversion, the gate is becoming depleted, and okay, so the question was, is there some quantum effect also in the gate? But see, usually the gate is very heavily doped, so you would never actually invert the gate. You just deplete the gate, but you wouldn't cause an inversion layer to also form in the gate. The depletion within the gate, it just follows the normal. It's not a quantum effect. Basically, electric field, yeah, it's just like very heavily doped silicon. There's no quantum effects that are relevant here. Yeah. Okay, so let's go to today's lecture slide. So we're going to talk about the transistor at last, the MOS transistor, to be specific. Okay, so historically, as I mentioned, maybe if some of you heard some of my other talks, the MOS, the field effect transistor, the concept of a field effect as a means to implement a transistor was actually invented well before the very first transistor was demonstrated in 1947. So the very first transistor that was demonstrated was actually closer to that of a bipolar junction transistor. So MOS transistors were not demonstrated until the 1950s. Okay, but anyway, probably the very first patent that describes something that's similar to today's modern MOSFET is this patent that was issued in 1935. So what it describes is an electrode, number 6, that is used to, okay, so let me get a correct color here. So this is the control, this patent describes a control electrode that is electrically insulated from the semiconductor. Okay, so it does describe a semiconductor. And it describes how current flowing between two regions in that semiconductor can be controlled under the influence of the voltage on the control electrode. So this would be like drift current flowing under the influence of the control electrode. Okay. So just to start from the basics, a transistor is a device. Usually, it's just simply it's a 3-terminal device where the current flowing between two terminals, so here, number 1 and 2 in this example, is controlled by the voltage or the current on a 3rd terminal. Okay, so that's just a simple definition of a transistor. So it's a transfer resistor. So you basically are effectively adjusting the resistance between terminals 1 and 2 by adjusting the voltage on terminal 6 in this case. Okay, so that's the basic transistor. Okay, so a little bit of review. Remember, we just covered the MOS structure for a p-type semiconductor. So that would be for an NMOS type of device. I just wanted to review. As long as you're changing the gate voltage, what you're doing is you're changing. Just notice how the electron potential energy is changing as you change the gate voltage. So as you increase the gate voltage, let's see, going to the right here. Okay, so these energy band diagrams are not all lined up. So let's imagine that the energy band diagrams all drawn so that, let's say, the edge of the valence band is sort of at the same level for all three, so you can just see what's going on. So as you increase the gate voltage, what's happening to the electron potential at the surface? It's increasing or decreasing? Decreasing, right? So you're basically making it easier for electrons to exist at the surface of the semiconductor by applying a positive voltage on the gate. Okay. So, but notice, as you go deeper into the semiconductor, it still becomes p-type, right? So only at the surface are you making the semiconductor n-type. So in a metal oxide semiconductor field effect transistor, when you turn it on, the current is only flowing at the surface, or very near the surface, in that inversion layer, which is about 1 nanometer or 2 nanometers away from the oxide interface. Okay, so in an MOS, or in a MOSFET, basically you apply a voltage to the gate, and that induces a vertical electric field, which affects the potential in this semiconductor at the surface, lowering it so that now you can have electrons flowing easily into and out of the N+ regions adjacent to the MOS capacitor. Yes, question? That's a good question. So what makes the electrons want to go from the left to the right? That's the fact that, so this is usually a transistor is a symmetric structure in that you have heavily doped electron regions, electron-rich regions, N+ regions to the left and right. So it looks symmetric. So you're right, current can actually flow in either direction. And what determines the direction of electron flow is the voltage difference between these so-called source and drain regions. So the source is defined to be the region that's supplying the carriers, so in this case supplying the electrons. And the drain, so this is the source on the left in this particular example, and the drain on the right. So the drain is the one of these doped regions that is sort of collecting the majority carriers from the surface. Okay, but this is only because the drain voltage is higher than the source voltage. Okay, so that's how you determine. As fabricated, you cannot really say which side is the source, which side is the drain. You have to see how the voltages are applied to the transistor to tell for sure which side is the source and which is the drain. Now, with the MOS capacitor, we have this the bulk silicon portion of the capacitor, and typically that is biased at some fixed potential V sub B. Okay, and as indicated here, I guess typically for an N-channel transistor where the carriers flowing from the source to the drain are negatively charged, so it's called N-channel, V sub B is grounded. Okay, so can anybody explain why V sub B is usually grounded or ideally grounded for an N-channel transistor? I'll tell you, basically, we only want current to flow between the source and the drain when the gate voltage is higher than the threshold voltage for a MOSFET. We do not want current flowing into or out of the source and drain regions otherwise. Yes. Okay, so that is one. So that the suggested question answer was, well, if you change VB to be non-zero, then that would affect the threshold voltage of the gate, which is true. Okay, but okay, that is a reason not to bias it other than at ground. Oh, is there going to be another suggested answer back there? Yeah.
Well, you have PN junctions between the source drain and the
Exactly.
reverse bias.
That's right. So it turns out you have these, well, naturally you have these PN junctions here. And you really don't want to ever have current flowing between the body and the drain to cause the drain to start to conduct current. Okay, so to ensure that this PN diode, this body to drain PN junction diode never turns on, so assume that all of the voltages in your circuit are anywhere from 0 volts, which is ground, to supply voltage, VDD, which is on the order of about 1 volt. Okay, so assuming that any of these terminals in your circuit could be biased at ground, anywhere from ground to the supply voltage, VDD. Basically, this means that you would like to bias the body so that no matter if this N+ region is biased at ground or at VDD, there's not going to be significant junction leakage or junction current flowing. Okay, So that means that you would actually like to bias the p-type side of the p-n junction at the highest possible bias, because you never want to forward bias this p-n junction diode. Okay? That's the simplest reason. And later, we are going to talk about body biasing, slightly adjusting the body bias to tune the threshold voltage. So in some products, people do actually purposely bias the body to be not at ground. It could be positive, could be negative, slightly above, slightly below 0, to tune the threshold voltage. And that's actually on your homework, next homework assignment. But the biggest reason that we generally try to bias the body close to ground is just to avoid this p-n junction diode from turning on. Okay? Because we only want the drain current to flow if the gate is turning on the channel. That's basically the bottom line. Okay, so let's draw the energy band diagram for this structure. So let's draw the energy band diagram near the surface, along the surface, like across the channel like this. Okay? So let's draw the band diagram. And let's assume that VDS is greater than 0. Okay, so that the drain voltage is at a slightly higher voltage than the source voltage. Okay, so both the source and the drain are N-type doped, right? So we can draw, Fermi level up here, like this. And this is EV. Okay, so let's say this is the N plus drain. We have we have the N plus source, N plus drain on the right, N plus source on the left. Okay. So what is going to be different between the source and the drain here when I draw the band diagram? I'm just going to make this neater. What's going to be the difference? Yeah, the drain will have a lower band diagram because it's at a higher voltage. So let's just draw that now. So we have the energy band diagram like this. But both are have the Fermi level at the conduction band edge. Okay, so how about the center region? It's a trick question, actually. What does the energy band diagram look like in the center region? Okay, it's a little bit of a trick question. Okay, let's assume VDS is small. But yeah, so there will be a little bit of slope because there will be some, if there's a positive voltage on the right, 0 voltage on the left at the end, so there's positive voltage on the drain, 0 voltage on the source, then there's a lateral electric field, right? So there must be some slope to the band. So that's very good, Ali. But at what height do I draw the energy band diagram? Yeah, that's right. It depends on the gate voltage. Okay, so let's draw for VG is 0 for now. Okay, so if VG is 0, what will be the state? Well, okay, let's say if VG is 0, let's say typically from your homework, do you remember like typically what is the threshold voltage? 0.7. Not that high anymore. But let's say at VG equals 0, the surface it's probably just depleted, right? Typically at VG is 0, the surface is depleted. Okay, so it will be still somewhat p-type, right? So basically, not going to be that high of a, so it'll be p-type. Okay, so let's just look something like this. Okay, so I was trying to draw this so that clearly there's a potential barrier because you have an N and a depleted P region here in the channel. Right, so you have a potential barrier height for electrons going from the N-type region to P-type region. But the height of that potential barrier is it should be less than the band gap energy, right? Because it's maybe only very slightly forward biased. Anyway, so it's depleted, but it might not be strongly p-type. Does that make sense? And so the band gap stays the same, so it should look kind of like a parallel line like this for the valence band edge. Okay, so this is for, let's say, VG equals 0 volts. Okay, so you have this potential barrier. So you have N-type region on the source, but sort of P-type, slightly P-type region in the channel. So you have this potential barrier for electrons to diffuse into the channel. So not very many electrons can diffuse into the channel. So negligible, we'll say for now, negligible leakage current between the source and the drain flows. Okay, yes, question? Yeah, so the question is, isn't the Fermi level for a p-type region near the valence band? Okay, so so this is p-type material. Oh, it's slightly depleted at, we're saying it's slightly depleted at the surface. So let's say the Fermi level, if we could draw one, would be somewhat, sort of here, right? If we could draw a Fermi level. We actually really can't draw a Fermi level in the channel region if there's an electric field there. But yeah, so if you imagine that there's let's say, a quasi-Fermi level, it would be roughly here, right, because it's a little bit p-type. And that would be kind of lined up with the Fermi level in the Okay, so let me draw a dashed line here. So this difference here, what does this difference represent? That's right. That's right. So it's QVDS. Okay, so that's in the off state. Let's draw it in the on state. So when we apply a gate voltage greater than the threshold voltage, surface becomes N-type. Okay, now from the homework that you just did, let's see. When you form an inversion layer at the surface, let's say the gate voltage is significantly above the threshold voltage. Do you remember how much inversion layer charge per unit area that was? Do you remember from your homework? So you should have found that it's, so the Q inversion, you should have found is on the order of 10 to the 12. On order of 10 to the 12. It depends on the gate voltage. Charges per square centimeter. So that's when you form an inversion layer at some reasonable gate voltage above the threshold voltage. Now, do you remember how thick that inversion layer is? It's about what order of magnitude? Nanometer. So the thickness of the inversion layer is about 10 to the minus 7 centimeters. So when you form a strong inversion layer, a reasonable inversion layer in the channel, what is sort of the average electron concentration per unit volume? So basically it's about 10 to the 19, right? To the 19 per centimeter cube of electrons. Okay, so when the transistor turns on, you have about 10 to the 19 per centimeter cube electrons in the channel. Usually the source and drain regions, when they're degenerately doped, the concentration of dopants is usually like 10 to the 20, okay, per centimeter cube. So you'll see a tiny little, 60 millivolt or so hump here. And so this is basically what the energy band diagram will look like when you apply a gate voltage that's significantly greater than the threshold voltage. So basically, the bottom line is this potential barrier for electrons to diffuse from the N+ region to the body region is eliminated. It's essentially eliminated. So it's very easy to have a flood of electrons diffuse into the channel region. Okay, so this is what we call the channel region, sort of up near the surface. Usually we call this region that's far away from the surface the body of the transistor. Okay? So qualitatively what happens is that as you increase the gate voltage to lower, so by increasing the gate voltage, you are lowering the potential barrier for electrons to diffuse into the channel region. And so current can flow under the, current can flow due to drift, due to the difference between the source and drain voltages. Does that make sense? So once you actually go above the threshold voltage, the current is not going to, in the transistor is not going to be limited by diffusion into the channel region. It's going to be limited by the rate at which carriers can drift across the channel from the source to the drain. Okay? So we'll derive a simple equation to explain for the drift current in the on state. Okay, in a modern transistor today, we'll explain later, probably in the next couple of weeks, why the source and drain regions are not perfectly roundly shaped. But this is basically the structure. The current flowing between the source and drain is controlled by the voltage on the gate. And ideally, very little current flows until you reach the threshold voltage. And after that, the amount of current that flows this is for a fixed VDS, say greater than 0. Okay, so the amount of current that flows, of course, depends on VDS, but it also increases as you increase the gate voltage. Okay, and the reason for that is because as you increase the gate voltage above the threshold voltage, what increases? Inversion. Inversion layer charge density goes up, so the channel becomes more conductive. So critical parameters, design parameters for a MOSFET are the gate length, which is roughly correlated to the separation between the source and drain junctions, the oxide thickness that we've been looking at already, and ideally, for a transistor to function well, you need, when you have a large gate voltage above the threshold voltage applied, you want the transistor to conduct a lot of current. And when the gate voltage is 0, you want the transistor not to conduct any current at all. And we have N-channel and P-channel flavors of MOSFETs, which can operate in a complementary manner. So this is why we call it CMOS technology. So I'll explain that in the next few slides. Okay? And Intel, well, it's just put into production last year some 3D transistor structures, but until then, the most advanced transistors were still planar. So you have silicon with a planar surface here for N-channel and P-channel designs. And the most advanced transistor designs have metallic gate materials. So these are actually metallic gate materials to minimize that to eliminate the gate depletion effect. Okay. All right. Okay. So in addition to N-channel and P-channel, okay. So a P-channel device turns on when the gate voltage is smaller than the threshold voltage. Okay. Or actually, to be more precise, the P-channel device turns on when the gate voltage is lower than the source voltage by at least the threshold voltage. Okay, so basically, notice when we talk about the gate voltage, it's always with respect to the source voltage. Okay, so that's an important fine detail here. Okay, so let's just review. Again, for an N-channel device, in order for current to flow between the source and drain regions, you have to apply a gate voltage that's more positive than the threshold voltage, or gate to source voltage that's more positive than the threshold voltage. Now, there's two flavors. There's enhancement mode and depletion mode. So if you have 0 volts applied to the gate, voltage, current flowing between the source and drain. There's two cases here. So in enhancement mode, you have this kind of switching behavior, like I showed on the previous slide. So here's the threshold voltage. And then in depletion mode, this is depletion mode. threshold voltage is less than 0. Okay. So name comes about that what matters is what's the state of the transistor when you have 0 volts on the gate. If you have no volts, 0 volts applied between the gate and the source, and the transistor is off, you actually have to apply a positive voltage to turn it on, to enhance conduction in the channel. So that's a normal enhancement mode kind of behavior. Now you can actually dope the channel surface. You can shift the VT, right, by implanting dopants, as we talked about last time. You can actually shift the threshold voltage so it's negative. So when you have 0 volts applied to the gate, okay, between the gate and the source, the transistor is already on, and so it's conducting current. And in order to turn it off, you have to deplete the surface of electrons, of those inversion layer electrons. So this is why it's called depletion mode. So bottom line is depletion mode is normally on, and enhancement mode is normally off. Normally means like when no voltage is applied. Okay? So we have the same analogy for the PMOS. Okay, so let's plot the magnitude of the current as a function of the gate voltage. All right, so remind me then. So let's say for enhancement mode, is the threshold voltage, well, it's going to look like this, right? This is enhancement mode. So how can we tell that it's enhancement mode? That's right, there's no current flowing with 0 volts on the gate relative to the source. And then for depletion mode, it's going to look like, well, something like this. If I can draw a straight line. Okay, does that make sense? So it's at 0 volts on the gate, it's actually on. Okay, questions? So there's 2 flavors of transistors. NMOS turns on with more positive voltage on the gate compared to the source. PMOS turns on with more negative voltage compared to the source. And then depending if it's on with 0 volts on the gate, it can either be enhancement mode or depletion mode. Okay, so this is summarized here. Any questions on enhancement versus depletion mode? Depletion mode just means normally as fabricated, because of the way you dope the channel region, there's already a conductive N-type layer at the surface. Okay, so you have to apply, like, for NMOS, you have to apply more negative voltage to turn it off. Okay, so before we talk about introduce the basic operation of a MOSFET, it's good to look at how these MOSFETs are used in circuits. Okay, so think of the MOSFET, a transistor. An analogy would be like a gate. Okay, so let's say if I were to ask you, okay, build me a gate. That's like you have to ask for some information, right? So like you have to, what kind of information do you need to know? If I ask you to build a gate and before you build it, what would you have to know? Budget? Okay, yeah, that's very practical. That's true. But how about even some, let's say, functionality-wise? I mean, you need to know how it's going to be used, right? So you need to know if it's going to be decorative, so it doesn't have to really keep out any intruders. You have to know like how many people, maybe per unit time, it has to be able to support. So you need to know how big it is, how strong it is, and so on. So same thing for transistors. It's important for you to know actually how transistors are used in circuits. So today we'll just focus on digital electronic circuits, so that you'll understand why it's not trivial to design a transistor to meet performance specifications all the time. Okay, so to explain how transistors are used, basically it's helpful to have these little circuit symbols. So on the left, I show the circuit symbol for an N-channel MOSFET and P-channel MOSFET. Different textbooks use different conventions, but the key thing to note here is the circle on the gate, right? The circle on the gate electrode, oh, I guess I didn't draw it here. Okay, so this is the gate. Hopefully this makes sense. and the source drain electrodes. So hopefully this makes sense that the gate is electrically isolated by a dielectric from the channel, which can connect the source and drain regions together. Okay? So the PMOS device is denoted with a circle on the gate. So okay, so CMOS circuits always have a complementary pair of NMOS and PMOS transistors. So this is a very simple, basic CMOS circuit where you just have one PMOS transistor and one NMOS transistor. Notice that their gates are tied together. So this is what we refer to as a complementary pair. And in this particular case, the source of the PMOS device is biased at the highest possible potential in the circuit, VDD. And the source of the NMOS device is biased at the lowest possible potential in the circuit, which is the ground. Okay? And the drains are tied together. Okay, so this forms a basic CMOS circuit. Okay, in practice, there are actually 4 terminals, for a MOSFET. So tell me, where do you think the body region of this MOSFET should be biased? At ground, right? So it'd be nice. Well, so usually the body of an NMOS device is grounded. How about the body of the PMOS device? VDD. It's the same thing. Because the source is P-type, and the body is N-type. And you want to make sure that that the body, the source, and the body of the drain, PN junction never turns on. So you basically want the N-type body to always be biased at the highest possible potential. Okay, so the drain can never be biased at a higher potential than the body to turn on that PN junction. Okay, that's good. All right, so what are the roles of these 2 transistors? So just look at so this is the output characteristic, the output voltage plotted as a function of the input voltage. So let's just concern ourselves with 2 points today, 2 extremes. When the input voltage is at VDD, this gate to source, so VGS equals VDD for the NMOSFET. Right? Okay, so this is a convention. VGS means VG minus VS, right? So VGS for the NMOSFET is equal to VDD. So that's greater than the threshold voltage. So typically the threshold voltage is maybe 1/3 of the supply voltage, just to let you know. Just very roughly, it's 1/3. So if VGS is equal to VDD, that means it's definitely above the threshold voltage. So that's why the NMOSFET is on. What is VGS for the PMOSFET? 0. That's right. Oops, why? My pen's not working. That's right. So if the input is high, then the difference between the gate and the source for the PMOS is 0. Right? So the PMOSFET doesn't have any negative gate voltage applied relative to the source, so the PMOS is off. So basically then what you have as a circuit is you have ideally an open circuit between VDD and the output, and you have the on-state resistance of the NMOSFET, we'll call it R on, the NMOSFET, connecting the output node to ground. Okay? Right, so ideally the PMOS device is off, so there's no connection between supply voltage and the output. Okay? Okay, so notice when the PMOS device is off, what is the drain to source voltage difference for the PMOS device? VDS for the PMOS, what is that? Well, it's the opposite, right? Because VD, the drain is connected to V out. So what is V out? It's 0. And the source voltage is VDD. Okay, so it's basically when the PMOS device is off, the source drain voltage is large. Okay? So if we go back and look at the transistor in the off state, if you remember, usually when a transistor is in the off state, there's a big difference between the source and drain voltage. So basically, these green energy band diagrams on the right would have been pulled down more. Okay? How about for the transistor that's on? What is VDS ideal in steady state? Yeah, VDS for the N is 0. Okay. Okay, so that's one case. That's one extreme case when the input is high. When the input is low, okay, what happens? VGS for the NMOS is equal to 0, whereas VGS for the PMOS is equal to minus VDD. Okay, so therefore the P MOSFET is on, N MOSFET is off. But again, when you have, so you have some on-state resistance of the channel, the PMOS device that connects the output, V out, to VDD, and then you have the N MOSFET that's off. So there should be ideally no connection between the output voltage and ground. Okay? But then notice that the VDS for the N MOSFET is equal to VDD. And VDS for the P MOSFET is 0. So in other words, the key is, okay, so the key point here I wanted to emphasize is that when a transistor is off, it should conduct ideally no current. It should conduct no current even if a high, especially when a high voltage is, when there's a significant voltage difference between the source and the drain. Okay? Okay, so of course we can have more complicated logic circuits, not just an inverter. You know, the input in an inverter, if the input's high, the output's low, and if the input's low and the output's high. So that just inverts the signal, the input and input signal. You can have much more complicated functions, but generally, in a CMOS logic gate, all the N-channel MOSFETs are used to connect the output to ground for an appropriate combination. All the P-channel devices are used to connect the output to VDD. So if we go here, you know, when the transistor is on, okay, when a transistor is on, basically, when the NMOS is on, its job is to connect the output node to ground. When the PMOS device is on, its job is to connect the output node to supply voltage. Okay? So you can have more complicated combinations of N MOSFETs and P MOSFETs that work in a complementary manner, but bottom line is you always rely on the N MOSFETs to pull the output node to ground or connect it to ground, and only P MOSFETs to connect the output to high. Okay? So let's go over just a couple of simple examples. A NAND gate. The output of a NAND gate is only low if both inputs are high. Right? So let's say 1 represents a high voltage, and 0 is represented with a low voltage. So this would be like ground, and this would be VDD. Okay, so looking at this circuit, hopefully you can see that, okay, so first of all, complementary logic. So notice that for each input is used to drive one NMOS device and one PMOS device. Okay, so A drives one NMOS and one PMOS, and B drives one NMOS and one PMOS device. Okay, it's always a complementary pair. Now, let's just write this down. If A or B, let's just see how the PMOS devices work. If A or B is low, then what? What will happen to the PMOS devices? Well, okay, if then a PMOS device is on, and you're right, and therefore F is 1. In other words, the output F is connected to VDD. Right? That's basically what the PMOS devices do. So basically all the PMOS devices do is turn on if A or B or both are low. That's their job. Now, if none of them are low, then the PMOS devices are doing nothing. Right? Well, they're supposed to be off. Okay. So what is the NMOS's job? Is if A and B are high, then both NMOS devices are on, so that the output F goes low. Okay? So notice that NMOS and PMOS devices are connected differently in order to provide this complementary function. So you never have a PMOS device turned on at the same time. Well, you never have a path between VDD and ground in steady state, ideally, right? Because basically there's no combination of A and B that would allow you to turn on one PMOS device and both NMOS devices in this gate. Okay, let's look at a NOR case, a NOR gate case. So how does this work? If A and B are low, then both PMOS devices are on, right? That's when F is connected to the VDD. Okay, but then complementary. If A and B are, if not both of them are low. In other words, if either one of them is high, right? If either A or B is high, then at least one NMOS device on. So the output goes low. Okay, so this is how CMOS logic devices work. Okay, so when a transistor is off, it's supposed to not conduct current under large drain to source voltage. Okay, when a device is on, it's supposed to connect the output to ground with as little resistance as possible. Okay, that's the ideal case. That's what we mean when the on current is high. That means the effective resistance of your MOSFET inversion layer channel is low. Okay, any questions about operation of NMOS and PMOS? Okay, so one final thing is how do you just pass a signal? Let's say you would like to gate a signal, a voltage signal. It could be high or low, right? X can be high or low. It can be 0 to VDD. How do we, under certain, let's say with a clock signal, only when you want, you can pass information from X to Y. Okay, so this is called a pass gate. So how does a pass gate work? Well, the role of the NMOS device is, well, okay, so remember, well, how do we explain this? If A is high or true, then the NMOS device is on. Right? And this is A bar down here. Actually, also the PMOS device is on. So basically, you have the gating signal A and its complement driving this complementary pair of transistors. Okay, so let me write the other case. If A is low, then there's no connection, right? There's no connection between X and Y. Okay, but only if A is high, then there can be a connection between X and Y. Okay, so the question is, why do we need two transistors to make this connection between X and Y? I don't know if you've already learned this in EE130, but it doesn't hurt to review. when A is true, or when A is high, you're turning on both transistors. Okay? But why do you need, so let's say, what is the role of the NMOS device? Passes, does it work better to pass a high voltage or a low voltage? Let's put it this way, because X can be either high or low. Let's say high, X is low. Okay, so let's say X is 0. What is VGS here? Is equal to VDD, right? Okay, so it's no problem. Then this transistor can turn on with low resistance, and it can pass. It can connect X and Y. Let's say ground. Okay. Okay, so if X is low, then the NMOS transistor can easily connect X and Y together. Okay. But let's say if it's high. Okay, so if X is high, so let's say VDD, what is this VGS? 0. So is this NMOS device going to be on to connect X and Y? No. Okay, so let's look at the PMOS. This is PMOS here. What is this NMOS? What about the the PMOS device? When X is high, what is VGS for the PMOS device? Okay, so A bar is 0, right? If A is true, we're trying to pass a signal. A bar is 0. I mean, that means A bar is at ground. So we're trying to pass the signal. What is VGS for the PMOS device? It's negative VD, right? So VGS for the PMOS is equal to minus VDD. So the PMOS device is on, right? So the PMOS device is, so the PMOS can turn on to pass a high voltage from X to Y. So the purpose of the PMOS device is to pass a high voltage. Right? So this is digital logic. The voltage can either, the signal X can either be high or low. You want to be able to pass either a high or a low signal to Y. And so that's why you need both an NMOS and PMOS device to work, to make a pass gate. Okay? So that's basically how a CMOS pass gate works. Okay, any questions about basic, how transistors are used? Okay, so let's see then qualitatively how the MOSFET operates. If the gate to source voltage difference, this is for an NMOS. If the gate to source voltage difference is below the threshold voltage, then you have the surface region is depleted, right? Depleted. So you cannot have a continuous N-type layer at the surface to conduct current. So basically, as I highlighted before, there's a potential barrier to electrons to diffuse from the source into the channel region. But if you apply a gate voltage, a positive gate voltage, you lower the surface potential, the electron potential at the surface. So now electrons can actually diffuse into the channel region and form an inversion layer, right? So it has some charge per unit area, Q inversion. So now you can have a continuous layer of electrons at the surface, about a nanometer thick, connecting the source and the drain together. So if there's a source to drain voltage difference, then current can flow. And so charge can get transferred, and the drain voltage can become equal to the source voltage as charge is transferred. Okay? So the key here is that when a transistor is on, current flows by drift. When a transistor is off, in this case here, any small leakage current is limited by the rate of carrier diffusion into the channel. So in the off state, current flows by diffusion into the channel. But in the on state, current is actually limited by drift, the rate of drift of carriers from the source to drain. Okay. And if there's a voltage difference, then the drain is going to be at a different voltage than the source. And so there's going to be actually a change in the voltage along in the channel from the source to the drain. Okay? And yeah, so basically the channel potential, V sub C, here is equal to the source potential. For the channel potential here, Vc, is equal to the drain potential. And so in other words, the channel potential is a function of distance. I think, let me just see, it's what we call it. I think it's x, but anyway, okay. Yeah, I'm pretty sure we call it x. But anyway, so it's a function of distance. Well, actually, we call it y, right? Because we call this x, and we call this this direction, this distance y. Okay, so the channel potential is going to be a function of the position along the channel, for either from the source to the drain. Okay. All right. Yeah, that's right. Okay, so let's derive an equation for the on-state resistance. So the effective resistance between the source and drain regions when the transistor is on, RDS. Okay. So let's assume first that the drain to source voltage is kind of small. It's not too big. It's much less than VG minus VT. So here's a good basic equation to remember, that the current that a transistor conducts between the source and drain regions, okay, so IDS just means the current flowing between the drain and the source. That current is going to be proportional to the width of the channel. Okay, so it depends how wide your transistor is. Okay, the wider it is, the more current you can conduct. It depends on the inversion layer charge density. So the more electrons you have in that inversion layer, the more conductive the inversion layer is. You can think of it as, becomes effectively a higher electron concentration, right? And also, the current in a transistor depends on the drift velocity, the average drift velocity of carriers flowing from the source to the drain. So that should be, hopefully, makes very good sense qualitatively. Okay, so three things, just three factors: the width, the inversion layer charge density, and the velocity of those inversion layer electrons. Okay, so let's break down each of those. The drift velocity, this is just some mobility times the lateral electric field. Right? There's going to be some voltage difference between the drain and the source. So there'll be electric field laterally along the inversion layer. Okay? And the lateral electric field, if VDS is not very large, it's just going to be equal to the voltage difference between the source and drain divided by the length of the transistor. So in case I didn't show you earlier, the length is defined to be the distance between the source and drain junctions. Okay? So that's a channel length. Channel length, capital L. Okay, so you're applying some voltage difference. On average, you take the voltage drop, divide by the length, the distance across that voltage is being applied, and that gives you sort of an average electric field. Okay, so that's where this comes from, right? This is sort of the lateral electric field along the channel, the inversion layer. Okay, so now you have a current equation for current as a function of voltage. And so if you model the transistor in the on state as a simple resistor, you just take the ratio of the applied voltage and the resulting current, and that gives you the effective on-state resistance of your MOSFET. Okay, so hopefully it's not too confusing. The longer the channel is, the more resistance you have for current flow. The wider it is, the less resistance to current flow. The more inversion charge you have. So notice, we have this now, the C-ox effective. So this includes, gate depletion effect, the inversion layer thickness effect, and so on. So C times VG minus VT, that's the inversion layer charge density, right? The higher that is, the lower the on-state resistance. And the higher the mobility, the faster carriers move, so you have less resistance, more current that flows. So here's something that's a little bit new, is the mobility. What mobility value do we use? Okay, so it turns out that the mobility of electrons drifting in an inversion layer is different than the mobility of electrons just like drifting in, let's say, some heavily doped source drain region. So mobility of carriers just moving, in this heavily doped regions is different than the mobility of the same electrons moving through this inversion layer. Okay, why is that? Qualitatively, why do you think that's the case? Yes, John. So you're saying they're moving through a region of ionized? Yeah, so there are a lot of ionized dopants in the depletion region that can increase scattering, but that also exists in a doped material. You have ionized dopants all over the place too, right? But it's just the difference is the net charge is zero for a uniformly doped semiconductor. So that's not quite the biggest reason why mobility is different in an inversion layer compared to just a doped piece of semiconductor. Channel's lightly doped, and okay, so if the channel's lightly doped, then you would expect the mobility to be higher in the channel. Let me tell you, it's actually much lower in the inversion layer. Okay, so the difference is due to this. When you form an inversion layer, that means you're applying a gate voltage larger than the threshold voltage. I don't remember, did I ask you to estimate the vertical electric field? Maybe, maybe not. Okay. Can you estimate, when you apply a gate voltage across this capacitor, you're actually inducing some vertical electric field. Remember this oxide electric field? And therefore, there's some electric field in the silicon right at the interface. That electric field can be rather high. It's it could be on the order of a megavolt per centimeter. Okay, so basically, there's a vertical electric field that's sort of attracting the carriers to the surface. So let me go back. Let's review the MOS structure. Yeah, when you form an inversion layer, see, there's this high electric field, right? Steep band bending at the surface. That causes electrons to be attracted to the gate oxide interface. So as the electrons are are drifting from the source to the drain, they're actually not just scattering as normal, going from the source to the drain. They're actually bumping into the gate oxide very frequently. People have estimated it could be like terahertz or something. I mean, so very, 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 because of the strong vertical electric field, they're basically just bouncing off that interface. So they're being attracted to the interface, they scatter off it, move a little bit to the right, and then get attracted to the interface, and so on. So basically, they scatter off the interface quite a bit. Now, of course, the amount of that extra scattering depends on the vertical electric field. In other words, it depends on the gate voltage. So here is an experimentally derived plot for electron field effect mobility on the upper curve, and the lower curve represents the hole field effect mobility. As you know, the mobility for holes is lower than that for electrons. But you have, for NMOS devices, notice there's an expression here. VGS, difference between the gate and the source voltage, plus the threshold voltage, plus 0.2, that quantity, that total voltage, divided by 6 times the equivalent oxide thickness. Professor Hu here at Berkeley, he first published some papers showing that empirically that is a good estimate for the average effective vertical electric field in the inversion layer. Okay, so as you increase the gate voltage, you're increasing that quantity, and so you basically mobility degrades. Okay, so the stronger you turn on the transistor, the lower effective mobility becomes. And it's basically, when we do homework or exam calculation, we'll just give you this plot, but basically you just need to use that equation, VGS plus the threshold voltage plus 0.2 divided by 6 times the equivalent oxide thickness. Find out how many megavolts per centimeter that is. Typically it's around 1. And then you just follow this curve to find out what the field effect mobility is. And it is significantly lower than the mobility in just a normal doped semiconductor material. Because the electric fields, when you're applying a voltage across a doped semiconductor, the electric field is not that high. Okay, so as mentioned, yes, by John, yeah, coulombic scattering is important. Phonon scattering, lattice vibrations are important. But surface roughness scattering becomes more dominant at the higher vertical electric fields. So anyway, so you basically have to use this chart to calculate the on-state current or the on-state resistance of a MOSFET. Okay, so do not use the old charts for mobility for just uniformly doped semiconductor. Okay, so that's it for the resistance of a MOSFET in the on-state at low drain to source voltage. Okay, let me clarify here. So this expression down here, this equation, this is the effective vertical electric field for PMOS devices. Right? So this is for NMOS. So just make sure you're using the right scale, for NMOS devices and for PMOS devices. That's why there's arrows here. Okay, so that's how you use this plot. Okay, so one very common point of confusion is coming up right here. So what happens if you increase the drain to source voltage to be significant? Okay, so remember, as I mentioned, the potential in the channel at the drain end is equal to VD, right? But now, what if VD becomes so high that basically the difference between VG and VD is less than the threshold voltage, right? In other words, there's a gate voltage being applied up here, right? You have a gate electrode, you're applying gate voltage. Now the difference between this gate voltage and the channel potential, what happens if it's less than the threshold voltage? If it's less than the threshold voltage, you will not form an inversion layer at the surface, right? The gate to silicon voltage difference is not going to be, it's not greater than the threshold voltage, you're not going to form an inversion layer. So that's what we call pinch off, right? So once the drain voltage reaches VGS minus VT, the channel potential is not going to be is going to be so high that you're not going to form an inversion layer at the drain end. Okay, so that's the pinch off phenomenon. Okay, so let's review. So the drain voltage typically is greater than 0, right? Greater than or equal to 0. In this case, it's greater than 0. And how is the body biased? Again, it's 0, right? Okay. Yeah, okay, all right, that's fine. So the bottom line is, how is this p-n junction, the drain p-n junction, how is it biased? Is it forward biased or reverse biased? Reverse biased, okay? So the drain junction is reverse biased. Okay, and we have electrons here in the depletion region of that p-n junction on the p side. So are the electrons majority carriers or minority carriers in the p region? These electrons, are they minority or majority carriers where they are? Minority, right? Minority carriers. So what do we know about p-n junctions when they're reverse biased and there's a minority carrier that shows up in the depletion region? Gets swept across. So electrons, if they enter this pinch-off region, it's essentially the depletion region of this reverse biased p-n junction. Electrons, when they reach that pinch-off region, so they drift from the source through the inversion layer, and then they reach the depletion region there. They're just going to get swept across, and they're collected by the drain. Okay, so just because a channel gets pinched off does not mean that you cannot flow current anymore. It just means that you're not going to be able to apply more voltage across the inversion layer. Right? In other words, the maximum voltage that you can apply across the inversion layer, the maximum voltage is equal to VGS minus VT. Okay, so the more voltage you, so basically inversion layer, you will not be able to apply more than that voltage across it. And the length of that inversion layer is roughly always going to be close to the channel length. So so normally then, ordinarily when you turn on the transistor to form an inversion layer, you increase VDS, you can increase the lateral electric field, but eventually you will not be able to increase the lateral electric field in the inversion layer anymore because of this pinch-off phenomenon, and so current will saturate. So current still flows, but you can't increase it because you cannot increase the lateral E field across the inversion layer. And remember, it's this lateral E field across the inversion layer that determines the current, right, the velocity. Okay, so any questions about the pinch-off phenomenon? All it does is it limits the voltage that you can apply across the source, across the inversion layer. Okay, so maximum voltage equals VGS minus VT. So as you increase the gate voltage, you can increase this maximum voltage. So you can actually increase, so as you increase the gate voltage, you can increase this saturation, the level of current at which you're saturating, right? Because you can apply larger and larger lateral field to the MOSFET before the channel gets pinched off. What also increases with VG? So not only the maximum velocity due to the maximum lateral field, but something else also increases with VG. The charge, right? The inversion charge density, right? So Q inversion increases with VG, VGS increasing, and also VGS minus VT, this quantity, the maximum electric field that can be applied across the inversion layer increases with increasing VGS. So because of those two factors, the maximum current, so this is what we call the saturation current. So saturation current, we'll call it ID sat. The saturation current is proportional to VGS minus VT squared. Okay, so qualitatively, you should know this is the reason why the maximum current that your transistor can flow depends quadratically or superlinearly on the gate voltage, because not only you have more inversion charge, but you can get up to a higher drift velocity because you can have more voltage applied across the channel inversion layer. Okay? So you basically have to draw a separate current versus drain to source voltage curve for each value of gate voltage greater than the threshold voltage. Okay, so these are just curves for transistors in the on state. Okay, so what happens, one final detail, what happens when you increase VDS then beyond pinch off? So what happens here as I increase, so the channel becomes pinched off, the current no longer increases. As I increase VDS, what happens? Well, any extra voltage above this pinch-off voltage, VGS minus VT, gets dropped across that depletion region. Okay, so the width of that little delta L depletion region in the channel region of the transistor, that actually increases with VDS. Okay, so that's shown on this slide here. All right, so the length of this depletion region actually will increase with increasing drain to source, increasing drain voltage. Okay, and because of that, your inversion layer length, the length of your inversion layer will go down. Okay, so now you're applying, this maximum VGS. So you're applying VGS minus VT. That's the voltage at which that's the drain voltage at which the current saturates. So that's called the VD sat. So you're increasing. Okay, so VGS minus VT is the maximum voltage you can apply across the inversion layer. And if you make that inversion layer shorter, then you're slightly increasing the electric field, the lateral electric field. Right? You're dropping the same voltage across a shorter distance. And so if you're increasing the lateral electric field, you're increasing the drift velocity. And so if this channel length is actually, or if this delta L is significant, like on the order of several percent or 10% or more, if delta L is significant compared to L, then you can see a significant increase in current as you increase VDS above the pinch-off voltage, above VD sat. Okay, so the current depends on the length of the inversion layer, which is L minus delta L. And if delta L is small, you can write it like this. And the length of this depletion region is roughly linearly proportional to the voltage dropped across that depletion region. And then you can work it out that then you basically can write your current, the saturation current, as some constant plus a slope factor. So this lambda here is the channel length modulation factor. Okay, so basically, the effective inversion layer length is changing, and that's causing the current to go up, and so that's what lambda is modeling. Okay, so only if the VDS is going to be higher than, once it increases higher than the saturation drain voltage, then you can have this extra effect of increasing drift velocity if the channel length is small compared to delta L. Okay? Okay, so qualitatively, I hope this makes sense. Question? The question is, if you make VDS big enough, won't you get tunneling? Yes, so yeah, you could get tunneling. That's true. So in the MOSFET design project, you'll find for various reasons that to suppress leakage, you might want to dope this channel region or body region kind of heavily. But then, in the off state, you're going to have high VDS, right? So you have large drain voltage in the off state, and then you have this reverse bias P plus N plus junction, and you'll have breakdown. You're right. So you get tunneling. So you'll see that when you simulate transistor behavior, if you try to dope the channel too heavily, you start to see that the off-state leakage starts to increase, and it's because of tunneling at this PN junction. So that is a practical concern for modern CMOS devices. Okay, so final minor topic is body bias. So as I mentioned before, we could actually change. We don't necessarily have to ground the body region, and we can actually bias it to tune the threshold voltage dynamically. After manufacturing, we can just change the voltage applied. But let me just explain very basically, even if we ground the body, that there's this body effect. Okay, so let's explain this in the last two slides. So when you turn on a transistor, you form an inversion layer, and that inversion layer essentially is connected to this N plus region, right? The source region. Okay, if the transistor is pinched off, then the inversion layer is not really connected to the drain. But the inversion layer is ideally always connected to the source region. In the source region, if you're applying okay, so let's say you actually have let's say you do have a drain here, like this. So you can actually get a voltage developing across the channel. So it goes from, let's say, VS on the left up to VD on the right. And let's say for now we just ground the body. Okay. So now we've formed at the surface an N-type semiconductor material. In the body we have P-type semiconductor material, and there's actually a voltage applied between those two regions. Right? There's some more positive voltage on the N side compared to the P side. So that P, and so you can think of that vertical. So let's go back and look at the vertical MOS band diagram. Looks something like this when the transistor is on. Right, we've formed an inversion layer. I'm going to exaggerate here. Okay. So here's the oxide, semiconductor, metal. Okay, so the surface is, the bulk is P-type in silicon, and the surface is N-type. Okay, so EC or EF is near EC at the surface, right? This inverted. Okay, so I guess I didn't exaggerate this enough. But you see, there can actually be a difference here between the Fermi level in the bulk and the Fermi level at the surface. Now remember when we drew the band diagrams for MOS devices, I said you have just a single Fermi level in the silicon? Well, with this MOSFET structure, you can actually have a different bias applied to the inversion layer compared to the body. And the bottom line is then you can have more band bending in the semiconductor. Okay, it's like a p-n junction, right? You're applying a reverse bias. Yeah, reverse bias to this p-n junction, and this difference there is just going to be equal to Q times the channel voltage difference with the body. Okay, I'm going to not pay attention to it's the magnitude, okay? So any split in Fermi level between the bulk and the surface is going to be due to a difference in voltage between the channel and the body. Does that make sense? Okay, so so what happens when you have more? So bottom line is you have more band bending or more voltage dropped in the semiconductor. Okay. So when you have more voltage dropped in the semiconductor, the depletion width increases, right? So this is the width of the depletion region. So the depletion width increases. So that means the depletion charge in the semiconductor increases. So remember all this is equal to the depletion charge in the semiconductor. And so this is the voltage dropped across the oxide. Remember this last term, voltage. So again, so VT is just given by the gate voltage at threshold. Okay, so this is the gate voltage is equal to the flat band voltage plus the band bending in silicon plus the voltage drop across the oxide. Now the band bending in the silicon is increased by VCB, right? So the voltage drop across the silicon is increased, but also the voltage drop across the oxide is increased because when you increase the voltage drop in the silicon, you're increasing the depletion charge. So both of these terms here. So this is phi s, right? The voltage drop across the silicon. This is Vox. Both of those terms increases, and you still need to have 2 phi f to form an inversion layer at the surface. And that's when the gate voltage equals the threshold voltage. So basically, this reverse body bias, so this reverse body bias between the channel and the body, that effectively increases your threshold voltage. Okay? So next time, we're going to take into account this effect to further refine the, this current equation for a MOSFET. Okay? All right, have a safe Halloween, and I'll see you next week. Oh, so don't forget, there's a quiz at the beginning of next lecture.